Um, Now it's almost 15:30 CET or 12:30 UTC, and we have here Simón, all the way from Chile, and he has volunteered to just show the poster videos one after the other. He really thought, together with Alice, and I absolutely agree with them, that the posters deserved some more exposure. And so he very generously volunteered his time, his work to assemble all these MP4 that were uploaded by poster authors and have them on his computer and play them. So thank you so much, Simón. It's really appreciated. I'm sure the poster authors also appreciate it. So whenever you're ready.
Okay, so I will test it first. So I will start sharing my screen. Let me know if it works, and then I will restart the poster from the video from the beginning. So you should see it now.
Hello everybody, thank you very much for choosing to view my poster presentation. My name is Robert Nikuta. I am the project scientist for the Astro Data Lab Science platform, which is developed at NSF's National Optical Infrared Astronomy Research Laboratory. We are based in Tucson, Arizona. Astronomy has fully entered the era of really big data. At Data Lab, we host almost 100 terabytes. Hello everybody, thank you very much for choosing to view my poster presentation. My name is Robert Nikuta. I am the project scientist for the Astro Data Lab Science platform, which is developed at NSF's National Optical Infrared Astronomy Research Laboratory. We are based in Tucson, Arizona. Astronomy has fully entered the era of really big data. At Data Lab, we host almost 100 terabytes of astronomical catalogs and provide access to several petabytes of astronomical science images. My poster shows how at Data Lab we employ Jupyter notebooks to access and analyze these large data holdings. This is possible because of co-location of big data with compute resources, and this is indeed the major difference between a traditional data archive and a science platform. You never need to download any data, but you can instead perform queries, run data reduction and analysis, and visualization tasks right on the same platform. You do all this remotely using nothing but a web browser. As a great way to teach our users, at Data Lab we develop a large set of example notebooks, which every user receives with their account. The notebooks range from introductory level through complete science examples, technical how-tos, to notebooks geared towards education and public outreach. We also welcome user contributions and help users to get their notebooks accepted into the collection. We develop the notebooks on GitHub, and when a merge into the master branch is approved, a webhook is triggered to automate deployment onto our platform. We also need to make sure that the notebooks continue to execute correctly at all times. This can be a challenge since the datasets and the middleware software are being updated often. To help with testing, we have developed a workflow based on NB-convert and wrapped it in a Python package to make testing really easy. If you are interested to learn more, please examine my poster in detail and visit us at datalab.noao.edu, and if you like, register for a free Data Lab account. Thank you very much for listening to this presentation. Cheers!
Hi everybody, my name is Brent Shapiro-Albert. I'm a fifth-year grad student at West Virginia University, and I'm going to tell you a bit about a really awesome new Python package, open source Python package, the Pulsar Signal Simulator. So why do we have a Pulsar Signal Simulator? What is it? So Pulsar astrophysics is complex, it's computationally expensive, and if you're not doing things in an optimized way, sometimes it can take a lot of computing time, a lot of iteration and power. So we've designed the Pulsar Signal Simulator to be an open source, easy to use simulation software to simulate your data. This can be used for science purposes to test data processing pipelines, different algorithms, or for educational purposes to teach students about pulsars and pulsar science, play with different parameters, see really what they do and how the signal is affected, and be easy to use. It's extremely modular, so we have lots of different classes. We have a signal class that talks about the type of signal you're recording or simulating. The pulsar, you can put in different pulse profiles, different periods. We have an interstellar medium that lets you disperse the pulse, add scatter broadening parameters due to that interstellar medium. We have a telescope class. You can make your favorite telescope with different sizes, receivers, backends, and we even let you have utility functions to save the data in a PSR fit style format that's compatible with standard pulsar processing software such as PS Archive. We've already used the simulator to do some really cool science. We've been able to simulate full pulsar timing array style data, 12.5-year data sets for a couple pulsars in just about 2 hours, so it's really fast. You can run this on your laptop if you want to. And we were able to show through this not only that the simulator is really excellent for this type of simulation, but that there are clear covariances in pulsar timing array data that we're already seeing, such as between the dispersion measure and scattering delays, that really need to be taken into account for high precision pulsar timing experiments, such as detection of gravitational waves. This is only a small example of what the pulsar signal simulator can do. We're constantly evolving it, adding to it, adding new features to make more and more realistic data sets that will be used for verification with, again, pulsar timing array experiments to do these incredibly sensitive detections, again, like nanohertz gravitational waves. Please go on GitHub. It's open source, fork it. And if you have, play with it. If you have any questions, please email me and let me know. Thanks.
Hi, welcome to the GammaPi poster. GammaPi is a Python package optimized for high energy astrophysics. It has been proposed as the science tools for the next generation Cherenkov telescope array, but it is used by other experiments as well. Example, we use it extensively within HESS. So one of the important features of GammaPi is that it allows multi-instrument fitting, which is enabled through simultaneous fitting of multiple data sets. They can be from the same or different instruments. So you can have data from Fermilat, from HESS, from CTA, and combine the likelihoods together to do a joint fitting. So this allows to have incorporate systematic errors into the likelihood as nuisance parameters, thus leading to better estimates on the parameters. So if you look at GammaPi.modeling, models in GammaPi are a mix of temporal, spatial, and spectral models. You can do a simultaneous fitting in all of them combined. So traditionally, you would have to extract the flux points and then do a fitting in temporal profile, or you would do spectral analysis separately, a 1D analysis and a morphological analysis separately. Now you can do all of them together. And which is, so you can have energy dependent models, which is super useful for many areas of galactic physics and others, I don't know. This is, so, and how we do it is through this package called GammaPi.maps, which are ND cubes with two spatial axes and an arbitrary number of non-spatial axes. So GammaPi.maps enables easy operations on these hypercubes. And these maps are sufficiently generalized containers, so you can use them for sky maps, for instrument response functions, etc. So for validation and benchmarking, like since GammaPi is heavily in development, we have automatic testing using GitHub Actions for our performance benchmarks and validation of standard science results. So this has been a very brief introduction. I hope you would check us out on check out our docs page, join us on Slack, or you can see our development on GitHub. And for now, I hope to see you in Discord, and I'll be happy to take questions. Bye.
Hello, everybody. My name is Marina Vela Núñez, and I work with the Dr. Cristina Napish and Ricardo Smarelia. We all belong to the Astronomical Observatory of Trieste, specifically at the Italian Center for Astronomical Data. In our archive, we have a Nadir platform, which holds a large amount of data from different telescopes. For that reason, to manage the different human intervention from different hosts is complicated. Even Nadir has his own integrate login system for controlling data flow. It doesn't have any internal log system to keep records of everyday data manipulation from different hosts. For that reason, we are proposing this login system. In order, this login system helps us to answer the follow-up question: who make modification, the host, where and when a modification was done, and what was modified. If we are able to answer this question, we'll more easily arrive to the root problems. Here in the methodology, we are showing you the design of our database, which information we included in this database, and we are showing you here the logic of our application, because this is automated application integrated in a native system. When a user make a modification, this automatically all the data intervention information will be stored in a database, to make more easy the searching for problem. We are also putting here some most important software that we use to develop our application, and we are also showing you some result that some example of the result we obtaining with our application. Those are here. Please, thank you so much for your attention. If you have any question, don't hesitate to contact us. Thank you so much and have a nice day.
I'm Alice Allen, editor of the Astrophysics Source Code Library, and I'm presenting on making organizational research software easier to find in the ASCL and ADS. NASA writes software for many purposes, including astronomy research. The agency has made a lot of its software open source on sites such as the HESARC page on Goddard's website, code.nasa.gov, and software.nasa.gov. Searching many sites for NASA astronomy research software is time-consuming, and we found that searching ADS for NASA software returns 0 hits. We proposed a project to NASA to make it easier to find NASA software in the ASCL and ADS by modifying the ASCL to add a keyword field. This required changes to our database structure, input and editing forms, code entry display, and reports that ADS, Web of Science, and other indexers use to ingest our records. We're adding the keyword NASA to our existing entries for software developed or funded by NASA. We're mining NASA code sites, such as code.nasa.gov, for astronomy research software and creating entries for these codes in ASCL and tagging them with the NASA keyword. We're also tagging them with mission keywords. In addition, we're creating reporting mechanisms to easily view this software and see the impact of making it public. This includes creating an API, which Sita Malvaram is presenting in a poster here at ADAS, and a keyword search on the ASCL. NASA astronomy research software is now found more easily, not just in ASCL, but also in ADS. ASCL entries are citable, and citations to ASCL entries are tracked by ADS. This makes it possible for NASA to see not only what software has been enabled by making its software public, but also provides a measure of the impact funding software development can have on scientific discovery. The changes we've made to the ASCL as a result of this project also provides an opportunity to improve discovery of other institutional software, as seen here for some of the software funded by the Heidelberg Institute for Theoretical Studies. If you'd like more information, please contact me, and thank you very much for your attention.
Hello and welcome to this lightning talk. I am Patricio and I'm going to guide you through some of the latest features of the BIP Manager project. As any reasonable person, one of our greatest goals in life is to do as little work as possible. We want to optimize time-consuming tasks into simpler ones. So I'm going to give you one example of how to accomplish this. Consider this situation. Today is the last day of that big proposal. It's time to put together the text from everyone. This is no big deal, but then you realize that you have to merge all the citations, which is a very tedious task because you have to go over every entry in the files. So that is no fun. Even worse, you have to check for duplicates, which one is most current, and so on. Nobody wants to spend their time on that. But we can do better without sacrificing your time nor the time from your students. I present to you Bib Manager, a command line based tool to automate your bibliography needs. Let's take a look. Okay, suppose you have all your bib files in the same folder. Let's join them all together into one file. And now, with this single command, you can produce a sorted bib file, removing any repeated entries. If there are any conflicts, you can see on the screen and then decide what to take. And that's it. Now, if you want to cross-check your entries with ADS, just add this -ADS argument, and bosh, that's going to automatically update your entries from archive to their journal versions. So the duplicates are detected by DOI, ADS bitcode, archive, and key ID. A resolving protocol automates selecting ADS entries over others and journal over archive. Only otherwise it will bother the user. So, finally, I want to tell you about the Bib Manager database. Specifically show you the browser. A set of shortcuts provides easy access to interact with the database. As you navigate, you can see at the bottom the author, year, and title of the entries. You can expand an entry to see their full content. You can search through the database with tab completions to help you. You can open the ADS entry in the web browser. You can open the PDF of the entry if you have it on your system. If not, you can get it directly from ADS. And finally, you can select entries to save them to a file or print to screen. Alright, that's all I have. Bye!
Hello, everybody. My name is Marina Vela. I work with the Dr. Cristina Napish and Riccardo Smarelia. We all belong to the Astronomical Observatory of Trieste, specifically to the Italian Center for Astronomical Archiving. Here we are presenting a graphical using interface to restore corrupted data, a support for preservation and curation of astronomical data. In our archive, we have our own platform to receive data from different telescopes from different parts of the world. But sometimes in the reception, those data arrive corrupted. So they don't pass the test, and those data are ending in a database we call warning. For that reason, in this research, we are proposing a graphical user interface that helps us to recover as much as we can this astronomical data corrupted. And this graphical this interface is based in the FITS verify. Then this is astronomical tool developed by the NASA. It's a standard tool. This tool gives us a record of the situation of the image data. He gives us the fatal errors and warning errors. In this case, we concentrate in fatal errors, and we bring all those information into our interface, and we are guiding to the user step by step in order he make the necessary modification in order to recover this damaged data. Our main goal here is to make this data available for final user. This time we concentrate, as I told you before, we concentrate in fatal errors. But for our future work, we concentrate in resolve it, also the warning errors in order to make more accurate recovery. I'm sorry, this is too fast, but please don't hesitate to call us if you have any question about our research. Thanks for your attention.
Hello, my name is Simón Torres. I work for NORLab's Solar Telescope, and I'm going to talk you about my application, which is described in poster P1075. So in the last couple of years, we have been creating the Goodman pipeline. It's a package that implements routines for spectroscopic data reduction, and is designed specifically for the Goodman spectrograph, which is a spectrograph at SOAR telescope here in La Serena. So even today, the VNC desktop is still used as a way to allow remote users to connect and operate the instrument, visualize the data. And we wanted to explore another solution. So we went with a web application. So it is built in Django, and the idea here is to have all the raw files listed here, and then in the right, the sequence of the files produced in every step. So, for instance, we start with the raw file, which you can see the cosmic rays and the edges, and then the pipeline, which is implemented as an API, a web API, will reduce. So you see now it's more clean. Then it will extract. So you see there the extracted targets, and then it will calibrate in wavelength. So you see here. So, but one of the most important parts is the user management, because the VNC desktop does not allow any control at all. So the idea is here that the user will have access only to the data that it's supposed to have access. In this case, I have access to everything because I'm a staff user. But a non-staff user will see only their proposal. Also, the calibration files are available for everyone. So here we can create users. Add user. So we create a user. For instance, I will try to create Simón Torres, which already exists. So I fill all the data here, then create. I will receive an email to ask me to create a password, which will be restricted. Also, it can be a very simple password, and also we can control. For instance, I no longer have access to the application. I'm just disabled, or I can re-enable very quickly. And also we have the documentation for the API. It will be available also when we publish it. So that's it. Please view my poster.
Hello, my name is Eva Sciacca. I am an information technology researcher at the Italian National Institute for Astrophysics. And in this video, I am pleased to introduce the first delivery of the ENIAS space services into the European Open Science Cloud. The European Open Science Cloud, EOSC, is implementing the open science realization in Europe by providing researchers with a federated platform of services supporting the research communities along the data life cycle. The ENIAS project is driving the co-design, delivery, and integration into the EOSC of innovative thematic services in 3 research sectors: underwater, atmospheric, and space. These services will exploit existing EOSC services and the European open science ecosystem. The space community within ENIAS mainly include astrophysics and planetary scientists, as well as computer scientists and software engineers interested in computer vision and machine learning from the research and business sectors. The Space Viz service provides an advanced operational solution for data management and visualization, including virtual and augmented reality, adopting FAIR principles for making data findable, accessible, interoperable, and reusable. The SpaceMOS service makes high-quality images from the raw data captured by instruments, that is the map making, and for assembling those images into custom mosaics. Finally, the SpaceML service performs pattern and structure detection in astronomical surveys, as well as in planetary surface composition, topography, and morphometry, also including machine and deep learning techniques. Thank you for listening, and we look forward for your feedback on the first release of the ENIAS space services. Goodbye.
I am Laura Michel, Chair of the Data Model Working Group in the IVOA and leader for the Mango project. The concept of source is likely one of the most used in astronomy. In fact, it is used for anything that sends some signal from some location in the sky, real sky or simulated sky. Despite this popularity, there is no VO standard modeling what a source is. The reason is there is no source definition that works for all different astronomy fields. A source model that pretends to cover most of the use cases would necessarily look like a Swiss cheese. From a case to another, it will have either useless quantity or missing quantities, or more likely both. For example, a model that would support many different positions, let's say for different epochs or different frames, won't fit very well data with a single position. It won't fit with multi-position data either, if positions have other purpose than those proposed by the model. Nevertheless, the virtual observatory needs a standard ensuring a certain level of interoperability for source data. A survey made among data providers and client developers confirmed the heterogeneity of the science cases. It provided us with a list of concrete use cases that guided the Mango design. To be short, what we need is not a model describing sources. We need a consistent framework allowing clients to properly understand the set of parameters or data attached to a source. This is the purpose of Mango. Mango stands for Model for Annotating Generic Objects. For Mango, a source is basically an identifier with 2 docks. One dock for the parameters, such as position, luminosity, various flag, or whatever else simple quantities. The other dock is for the associated data, such as light curve or any sort of counterparts. The model does not specify which items are on the docks. It just gives a common interface to consume them. In parallel with the model development, we have been working on an XML syntax that can be used to annotate VO tables. The goal is to demonstrate that we can map archival data on the Mongo model. This mapping syntax has been designed to facilitate the annotation process and the human readability. It consists in an XML block located on the top of the VO table. This block contains elements reflecting the model structure. The references to the mapped data are set as attributes of the mapping elements. This mapping block can be seen as an interface between the client and the real data that ensures a good interoperability level. By parsing the annotations, the client automatically gets the data representations compliant with the Mongo. We have been testing this on data issued by XMM, Chandra, Vizir, and Gaia. So enjoy your poster reading. This is a poster P3-181.
Hi, I'm Adrian from the Music and Technology PhD program of the Polytechnic University and the Royal Conservatory of Madrid, and I would like to introduce the Python pipeline we're using in the sonification of Lightcure catalogs for the development of an astronomical data automatic music composition system based on deep learning.
FITS to OSC is a cross-discipline pipeline that reads the Lightcure information stored in FITS files and outputs OSC data through UDP protocol. It provides a user-friendly, non-time-consuming environment for both graphical and auditory exploration of a user-selected Lightcure from the Space Telescope Science Institute archive. In this example, we will explore one of the Kepler-1661 eclipsing binary system Lightcures fully described in Socia et al. We will use a simple sine wave oscillator with x-coordinate mapped to the timeline and y-coordinate mapped to the sine wave frequency. Acting over v variable, we can change the playback speed. Using t and I range variables, we can focus the attention in any area of the light curve. Now, we can see and hear a transit of the exoplanet Kepler-1661b in the flux variations of its host eclipsing binary star system. In this simple way, the FITS2OSC pipeline opens the door to the multimodal exploration of Lightcure catalogs to be used in both astronomy and music applications.
For any question or discussion, please contact by email. Thanks so much for your attention and stay safe. Bye.
Dear astronomers, researchers, engineers, ADAS organizers, and any other of eager to learn curious nature, it is my pleasure to present to you GW Sky, an augmented reality mobile app for the localization and visualization of gravitational waves. My name is Valerio Tonelli, bachelor's degree in computer science, and currently studying artificial intelligence in Bologna. The app, which you can see on screen right now, has been developed in collaboration with the University of Urbino Carlo Bo, the ENFN, the HAHED 2020 project, the Escape H 2020 project, and the Rainforce project. From the main menu, we can reach the list of gravitational events. Currently, there are only a few for demonstrative purposes, but we do plan to add connectivity to the LIGO, Virgo, and Kagra database of gravitational events and, potentially, even notifications upon detection of new signals. With a tap, one can download or remove an event from the local storage. By tapping instead on play, and after a short period of loading time, a majestic view of the stars and galaxies is open to be explored. This virtual sky is aligned with the local sky of the user, so that the view shown on the device, by orienting it in some direction in space, matches the one which could be seen, effectively or hypothetically, at that same direction in the real world. Like a stargazing app, but with the advantage of the photospheres coming from proper astronomical surveys of the sky, converted from the HIPS formats. And as we follow the arrow in the bottom of the screen, we reach a region of the sky in which the specific gravitational event we have loaded has come from. Most likely, at least, it is a probability map converted into an image from the MOC format.
W150914 LIGO Hanford data.
And here is the app with a different, more picturesque photosphere. As of today, the app is clearly targeted towards science divulgation. However, we do plan on adding much more detailed data about each gravitational event, ones that an expert of the field may expect, including graphs, tables, etc. If you wish to know more, I recommend that you take a look at the corresponding poster or the paper once the proceedings come out. Albeit our journey into this gravitational sky has been short, I hope that you have enjoyed it, and I wish you a great continuation of the ADAS 2020 conference.
Hello, have a good day, dear colleagues. Me and my colleague Sergey Kotov and our research supervisor Sergey Nikolaevich Dodonov are pleased to present our work, Optical Identification of X-ray Sources in the HS 47.5+22 field. For our research, we use data from the Rosat X-ray survey. For optical identification, we use data from a medium-band photometric survey that we conduct for 2 years on the 1-meter Schmidt telescope at the Barakan Astrophysical Observatory in Armenia. To cover most of the fields observed on the Rosat, we observed 4 positions with an overlap of about 10 arc minutes and created a mosaic with a total area more than 2 square degrees. Each of the positions was observed in 4 broadband and 15 medium-band filters. Photometry of object is performed using 6-structure and a dual image mode. For photometric calibration, we use spectral and photometric data from the SDSS survey. Thus, we excluded the influence of changes in photometric condition during observation. The completeness of the object sample along the stream is determined by the depth of the reference image used to determine the coordinates and geometric characteristics of objects. In this way, we can expect no color selection over the entire wavelength range and a complete sample of objects up to 23 magnitude in the R filter. We have developed and tested methods for constructing the spectral energy distribution for objects based on the observation in medium band filters, as well as an original method for analyzing the spectral energy distribution, which allow us to classify objects and estimate their photometric redshift with an accuracy better than 0.01 for all types of galaxies and 0.03 for AGNs. For optical identification, we took data from the Multikin catalog. A box of errors in the position of X-ray sources is the radius 3 sigma plus 10 arc seconds. It should be noted that for our optical data, there are 2 values that determine the identification of X-ray objects. First, it's a limit value for detecting object. And second, and the limit value for classifying and determining photometric redshift of the objects based on their spectral energy distribution constructed from medium band filters, which depends on the spectral type of object. The field covered by optical observation included 144 X-ray objects. We couldn't classify 11 objects. As candidate objects for optical identification, we selected objects with a wide emission lines, its quasars, galaxies with active star formation, and galaxy clusters and stars if we don't have another candidates in error box. And in the final, with the detection hour limit and our limited flux, almost 50 of the X-ray error boxes are filled with more than 2 objects. And this significantly complicates the subsequent interpretation of the result. That's all. Thank you for your attention.
Hello, we are Jaime Rosado and Daniel Morcuende from Universidad Complutense de Madrid. In this video, we present a new tool called Shower Model, a Python package for modeling cosmic ray showers, their light production and detection. The package allows for the fast calculation of signals of both Cherenkov and fluorescence light from air showers, as they are observed by an array of telescopes. This array can be configured as fluorescence telescopes. Imagine atmospheric Cherenkov telescopes or any hybrid design defined by the user. This tool can be used to speed up cosmic ray studies that do not require a full simulation, and also to check and complement complex simulations and data analysis. Shower Model is open source software that is available through this GitHub repository. At the moment, the repository is private, but we will make it public soon, including some GitHub pages for documentation that are under construction. The package comprises several modules and classes to describe the different aspects of the air shower development and detection. For example, the atmosphere, the shower longitudinal profile, the telescope, and so on. The code is well annotated and documented with docstrings. In addition, the repository has also several Jupyter notebooks that span on different use cases of the package as kind of tutorials. For example, this notebook describes how to produce camera images. An air shower is generated in this simple way, where the default energy and type of the primary particle are used in this case. This is a default Cherenkov telescope, and here the light signal recorded by the telescope is computed. Afterward, camera images with different options are generated. Below, some images are shown. First, for a Cherenkov telescope, and second, for a fluorescence telescope, observing an air shower sideways. Finally, you can see the case of an array of Cherenkov telescope observing an air shower at different core distances. To conclude, we want to remark that the code has the distinctive feature that can compute both Cherenkov and fluorescence light production in air showers based on the parameterization described in these references. Shower Model provides a versatile tool to explore new observatory configurations and detection techniques that exploit both light components. Thank you for your attention. We are pleased to receive your feedback. Please contact us.
Hi everybody, my name is Alessandra Berretta, and in this poster I will show a practical way to search for spatial and temporal coincidence between Fermi-Latte exposure maps and gravitational wave events by LIGO and Virgo using a technique called multi-order coverage that compute coverage regions from sky maps using pixel tessellation. So now I'm going to show you just a quick tutorial on how to obtain these mock maps. So here you can see the Aladdin interface divided in 4 canvas. In the first one you can see the sky seen by Fermi, then the gravitational wave event of 170104, then the Fermi-Latte exposure map obtained 10,000 seconds after the gravitational waves trigger, and then the 31st energy beam of the Latte exposure map. To obtain your spatial mock, you firstly have to select the most exposed pixel, so you have to select on pixel button, then CM on view, and a bar will appear. From this bar you can select your pixel, so we decided to select all the pixels that have values greater than 10 to the 7. So after that, you can click on coverage and then generate a spatial mock based on the current image. And then you have to insert your values here and then create. And then in red, you have your spatial mock. So after that, since we want to obtain a space-time mock, you have to read from the feeds file your starting and ending time of the observation. So you have to click on edit and feeds header. And from here, you can copy your starting and ending time and insert after clicking on your mock on coverage, and then generate a space-time mock based on the select space mock, and then click on apply. After that, you can see the temporal extension highlighted in red of the Fermi-Latte exposure map. So we can do the same thing for the gravitational waves event. So we can click on coverage and then generate a special mock based on the current probability sky map, fixing a probability threshold of 0.9, and then create. So after that, in blue, you can see the mock map related to the sky map of the gravitational wave events. So we want to create again the space-time mock, so you have to click on the SkyMap fits file, and then on edit, and then on fits header. And from here, you can copy your gravitational waves time trigger, and then insert after clicking on mock, on coverage, and then generate a space-time mock based on the selected spatial mock. And then apply. And after that, you can see in the time plot that a blue line has appeared and it refers to the gravitational waves trigger. So after that, we want to compute the intersection map between these two sky maps. So we have to click on coverage and then logical operations, and then we have to select the planes between which we want to compute the intersection map, and then we have to click on create, and then after that, in orange, you can see your space-time mock of the intersection map, and also in the time plot, you can see an orange line that represents the temporal intersection between these two maps. So you can access temporal and spatial information of your mocks just hovering over the cursor over the mock maps in the Aladdin stack, or right-clicking here and then properties, and then a window with all the characteristics will appear. Of course, the analysis can be done using different sky maps coming from different experiments. And thanks for your attention.
Hello everyone, my name is Mauricio and I'm part of the NRA Online program, and this is the BLS Quick Look Image Classifier using PyTorch. BLS, or the Very Large Array Sky Survey, is expected to catalog approximately 10 million radio sources with corresponding Quick Look images. BLS Quick Look images, like the one shown on Figure 1, can be used to train a neural network classifier using PyTorch. PyTorch is an open source machine learning library and using applications such as computer vision and NLP, or natural language processing. We can also take advantage of PyTorch tensors, which are n-dimensional arrays, and can be run on GPU to speed up our training and classification times. We use a neural network which consists of multiple input layers and multiple hidden layers in between, and one or more output layers corresponding to the number of classification categories we have. Every node on the network is connected to every other node, and each of these takes the weighted sum of the inputs and runs it through a function, which in itself is connected to another node in the next layer. We can also use an activation function, such as a sigmoid function, to determine where in our classes list the image we're trying to analyze belongs. The steps to classify the images are as follows. First, we split our datasets into our categories. For this classifier, we use a classification list of single, multiple, and diffuse sources, like the one shown on Figure 4. We split the total amount of images into a training dataset and a validation set. After that, we can run our training dataset through the classifier to try to make it learn the parameters that correspond to each of the classes we have. And finally, we can use our validation dataset to try to make our model classify the images correctly and use a true-false comparison to a known class. In this case, we can tell whether the image is a single source class or not via the true-false comparison shown on Figure 5. For this example, we can see that the model correctly distinguishes between a single source and its actual value. For the first image, we have an actual single source, like the one shown here, and its actual value. For the second image, we have a multiple source, predicted as being false to being a single image. And at the third image, we can see another one of the single sources correctly classified. Thank you.
Hello, my name is Shabir Bawaji and I'm from ThoughtWorks Pune. Along with me Ujjaini Alam, who is from ThoughtWorks as well, and Shurajit Mundal and Divya Oberoi, who are from NCRA TIFR, have been collaborating on exploring coronal heating using unsupervised machine learning. An enduring mystery about the sun is that the corona, the atmosphere of the sun, is at a temperature of a few million kelvins, while the surface of the visible sun is at only 5,800 kelvins. A promising solution to this coronal heating problem is the nanoflare hypothesis. A large number of very small flares take place all over the Sun all the time. Individually, they are too small to be observed, but collectively, they can heat up the corona. This work is inspired by what is perhaps the very first detection of radio signatures of these nanoflares and aims to study their morphology. We work with 8,000 radio images taken every half a second at 132 MHz from the Murchison Whitefield Array in Western Australia. An earlier study found over 33,000 of these weak, impulsive, narrow-band quiet sun emissions, or WINKs, in this dataset. Here is one of the images of the Sun from the dataset. What we see here is the active region and want to exclude this region from our study, as the WINKs are found in the quiet region of the Sun. Within the quiet region of the Sun, we see that these are the isolated peaks and resemble to a Gaussian model. These are the clustered peaks and they don't resemble the Gaussian model, and therefore a Gaussian model doesn't fit well here. To identify the isolated and the clustered peaks, we have used dbScan and clustered these peaks based on their positions. Then we fit the Gaussian model to the isolated peaks, and as we see, we get a very low residual which ranges between -8 to 8%. The Gaussian model parameters quantify their shape, size, and orientation. This study shows that the area of the Gaussian model and its width along the major and minor axis show that their emissions are quite compact. Median of the area is nearly 24 units, and the median of the width along the major axis is nearly 4 units. This matches the theoretical expectations. We will be applying this approach on various other radio solar datasets. The current dataset is a function of space and time. In future, we would like to extend this approach to space, time, and frequency, as the telescope is capable of taking these images in various frequency bands as well, within the radio spectrum. We can then study the evolving morphology of these solar structures over space, time, and frequencies. Thank you, and please feel free to reach out to me during the conference.
Hello, ADAS participants. My name is David Shoup. I'm a scientist at the Infrared Science Archive at IPAC on the campus of Caltech, which you see in my virtual background behind me. I'm also a member of the AstroPi project. Got my core team hoodie on. But today I'll be talking about our use at URSA of the Astronomy Extensions for SPARC framework. We've been collaborating with University of Washington and Dirac Institute, who developed this framework. And we've been running this to process the NEOWISE data. NEOWISE individual source exposure table has 114 billion individual measurements piled up over 6 years for about 1 or 2 billion objects, and we'd like to make those into light curve products. In the middle shows our workflow. Currently, we serve for bulk downloads these catalogs in compressed separated value format, compressed with bzip2. SPARC reads those very easily in parallel, and then we save those into Axis tables. Axis saves those in Parquet format into 1 arc-minute zones sorted by right ascension with a little bit of overlap region where the data are duplicated. And those zones are spread over the Parquet partitions, which turn out to be individual Parquet files, all over the sky to speed up the cross-matching. Once we have the data in that format, we cross-match to the preliminary CatWise catalog. We did half the sky for this prototype, so it took only about 10 hours to do the 250 million light curves. And here you see an AGN light curve at the bottom. To do a basic cross-match, it's only a few lines of code and you get this powerful parallelization. You can just head on down to the lower right part of the poster where you'll find the documentation, the GitHub, where you can see where things that the group is working on, and an astronomical journal paper. Thanks for stopping.
Hi, my name is Radek Poleski, and I'm from the Astronomical Observatory, University of Warsaw. I'd like to present a software called Mullens Model, which I developed together with Jennifer Rhee from Harvard-Smithsonian Center for Astrophysics. The goal of the Mullens model is to allow fitting planetary microlensing models to the light curves from the future NASA flagship mission called Nancy Grace Roman Space Telescope, formerly WFIRST. Roman telescope is now under construction and is similar to the Hubble Space Telescope, but Roman's infrared camera has a field of view that is 100 times larger than Hubble field of view. So why microlensing research is hard? There are two main reasons. First, calculating even a single model light curve is relatively complicated. Second, while fitting the models, we frequently approach parameter space that has multiple degeneracies, which can be both discrete and continuous. Hence, we need a software for fitting models relatively easy. In the middle of the poster, I'm showing the simple usage example of Mullens model. These few lines of code calculate the light curve of a microlensing event where the lens system is a star with a planet. I'm showing the calculated light curve, and at the bottom of the panel I'm showing the trajectory of the source relative to the planetary caustic and the stellar caustic. You can see the planetary anomaly, and you can see that it happens when the source approaches the planetary caustic. If you want to see this light curve without the planetary anomaly, just remove SQ alpha and you run this code. The right column describes some of the Mullens model properties. Most importantly, it has a link to the GitHub repository. Please check it out. If you have questions, please contact me via email or on Discord. Thank you.
Hi everybody, my name is Marco Molinaro. I'm the IVOA Data Access Layer Working Group Chair, and with my co-chair James Dempsey, we have prepared this poster contribution. We did it to describe the status and ongoing activities to standardize discovery and access for astrophysical data resources. That is, the data access layer goal. To do that, we prepared 3 diagrams that I briefly show you here. The first is an architecture diagram. It places the data-related standards in the global IVOA architecture and provides a hint on new specification on the recommendation path, as well as ongoing revisions. New and revised specifications that our members are working on are balanced in number by the stable ones, or better, by those waiting for community feedback to progress. The roadmap diagram shows in more detail how the specifications are expected to progress in the next half a year. You can see a set of standards is expected to grow mature, with new specifications entering the roadmap. Still, many standards are in standby. That is, they require feedback. And this is where the contribution from data providers and projects play a major role. To help contributors take up the data-related IVOA recommendations, this dependencies graph reports how the standards are connected among them. You can see the interface basic factorization provided by DALI. Some older standards haven't yet been updated to comply with it. And you can see TAP support for data model-driven discovery. Please have a look at the poster's PDF. It links to a preprint on the proceedings and gives some extra information useful when taking up DAL standards now and in the near future. For any other detail, please refer to the links and contacts listed here at the bottom. Thank you for your attention.
Hello, this is lead author Graham West. Allow me to give you an overview of our poster. Our main goal is to use genetic algorithms to fit models of internet galaxies to observation data. The main challenges to this process include the quantification of similarity between model and target images and the navigation of a complex and degenerate parameter space. Solutions to these problems include novel two-factor similarity score methods, as well as a characterization of the various symmetries, which allows us to reduce the degeneracy inherent to this parameter space. We use the SPAM or JSPAM a restricted 3-body simulation code. We also use in merge wars projects. These human scores can be used to develop and validate automated scoring methods. Early on in our research, we determined that naive scoring methods lead to very unintuitive rankings of model quality. As can be seen here, we have a given target image along with 9 merge wars models. One can see that the citizen scientist scores apply a reasonable and intuitive ranking of the model quality, but the naive fitness function, which is given by a simplistic 2D correlation, does not. As you can see, this model here is scored more high than both of these two, despite the fact that these two are clearly a better model of this than this one is. From examining the data, we discovered that the 3 main factors contributing to the poor performance of these naive functions all had to do with the presence and degree of tidal features. Therefore, our solution was to quantify the degree of tidal distortion and to include that as another term in our fitness function. This was done by creating a third image called the unperturbed model, which allows us to quantify regions of tidal features. We can then improve our naive fitness function by adding a weighting scheme, include logarithmic intensity scaling, and of course include the tidal distortion term. We can analyze the performance of these scores by comparing them with the citizen scientist scores. On the left we have our naive function and our citizen scientist scores, and we get a correlation of negative 0.189. Clearly the naive score system is quite poor. On the right we have our new complete scoring system, which gives a correlation of 0.754, which is fairly good. Moving on to symmetry, we define a symmetry as a span parameter transformation under which any model's morphology is invariant. The main problem this causes is that for any given target image, there is no unique solution which describes it. To summarize, we have one class of symmetries called geometric symmetries, which cause the parameter space to essentially be composed of multiple regions which are merely reflections of each other. We can therefore eliminate these reflections by reducing the range of these span parameters. We also have an extra dynamical symmetry, which allows us to essentially remove the total mass parameter when there's no VZ data. In conclusion, we developed an intuitive and robust fitness function which allows us to reproduce the quality of human scores from the merge wars project. We then used this function to identify various symmetries within the span system. When included in our genetic algorithm code, both of these improvements provide a drastic increase in the accuracy and efficiency of our optimization process.
And hi there. So this is a lightning talk presenting the on-site processing pipeline for the CTA large size telescope prototype. And I am talking on behalf of the LST-OSA team for the CTA LST project. So I guess you are aware of the CTA project. CTA will observe the most energetic events in the universe with telescopes sensible to the highest energies. This is done by observing Cherenkov light showers produced within the atmosphere by very high energy gamma rays coming from outside. CTA will be composed of 2 different arrays of telescopes, one in the southern hemisphere, another in the northern hemisphere. And the northern side is located in the Observatorio del Roque de los Muchachos in the island of La Palma at the Canary Islands. So there, 4 large-sized telescopes of 23 meters diameter each will be built. So, okay, the first prototype of these large-sized telescopes is called LST-1, and it is already built, and it is in the commissioning phase, and LST-OSA is responsible for the processing of the data on the site. So why on the side? So this is because of the large amount of data recorded, and it was thought that transferring all this data from La Palma to continental Europe through the internet was not a good idea. So an LST on-site analysis, that's why the acronym, was considered to perform the reduction of the raw data at the site. For example, LST-OSA performs the calibration of the data, calculates the geometrical parameters of the form, those nanosecond flashes produced in the camera, tells you the type of particle that has triggered the shower of Cherenkov light, if a gamma ray or a charged particle, in most of the cases is a charged particle, and it finally keeps only photons in the analysis to infer energies and directions in the sky of the gamma rays. And the different data produced across the pipelines are labeled as these different data levels here. And for doing this, LST-OSA heavily uses algorithms and scripts provided by LST-Chain. LST-Chain is the pipeline library for the analysis of LST data, and is also presented as a poster in this conference. So have a look at LST-Chain poster. LSTO also captures all the details of the workflow process into provenance text files following the IVOA provenance model. And this provenance capture is serialized as JSON files and PDF graphs. So that's all good news. LSTO is currently working at the LST1 site, helping with commissioning, performing data quality checks, and helping with debugging data analysis scripts. You may find more information in this link here, or you can send us an email or ping us on Discord if you need some more information. So thanks very much for your attention and enjoy ADAS.
Good morning, everyone. For those who don't know me, my name is Vito Conforti and I work in INA FOAS Bologna. The main scope of my work is software engineering for ground projects and space missions, but concerning the development and realization of software, my field is the data acquisition from astrophysics instruments. I'm here today to present the ASTRI project, the lesson learned from the prototype and the solution for the future steps of the project. ASTRI is an international effort led by the Italian National Institute for Astrophysics to design and realize an end-to-end prototype of Cherenkov telescope in dual mirror configuration. The prototype, we named ASTRIOR, is operative and installed in Sicily. The next step is to build an array of 9 telescopes which will be installed at the Teide Observatory in Spain. Our software has a receiver module which gets data packet by packet from the backend of instrument through a UDP direct connection. Then the packets are stored in raw format and managed by another software component, the provider, which groups packet by data type, science, calibration, housekeeping, and so on. Then, for each data type, a processor decodes and stores data in FITS format. One of the requirements for the data acquisition is support data rate of 600 events per second. But what happened is that during the commissioning on site, when the night is dark, but never always so dark, for the lucky of astronomers, well, sometimes the night sky background or other unexpected phenomena for which they exceed the configured thresholds of the electronic front end, then the data rate increases much more over the nominal rate. And this higher rate for a long time originates the failure of provider. We detected the bottleneck in the CFITS.io routine that writes data on FITS format. So, to fix quickly this bug, we decided to postpone the raw to FITS conversion offline after the end of the acquisition. The good news is that for the mini array, the data acquisition system is required to create the FITS format offline and offsite. Nevertheless, it's required to decoding and providing data during the acquisition to the online observation quality system. And then we start to investigate a solution based on Redis, which is an in-memory DB, and so we updated the software to write decoded data on Redis server instead of FITS file. From the functional point of view, it's run. Concerning the performance, we have the same execution time of the previous version in test environment. We will have a significant assessment of the solution, repeating the tests during the night to the ASTRIOR. Furthermore, we will improve the system performing a fine-tuning of the Redis server configuration, and eventually we will investigate a more performance Redis data type. Enjoy and stay safe.
Hello everyone, my name is Jonathan Kenyon and I'm going to be speaking to you about Cortical, a Python package implementing embarrassingly parallel calibration of radio interferometer data using NUMBA and Dask, and I'll get onto exactly what those are in just a moment. First of all, I'd like to provide you with some context for what Cortical is. Cortical is the spiritual successor to Cubical, another Python package implementing calibration, which was developed during the course of my PhD. Unfortunately, due to some limitations in Cubical, it is not entirely appropriate for scaling to terabyte-sized problems, and Cortical aims to address that. Just to provide some context for why we care about calibration, well, very simply, calibration errors in our data limit the quality of the images that we can produce and may in fact limit the science that we are able to do. As such, it is very important that calibration is both good and fast. The reason why that speed is important is because for instruments like the Meerkat and SKA, the data volumes are so fast that calibration becomes a processing challenge. Now, the way we aim to combat this is using a combination of Dask and NUMBA. What is Dask, you say? Well, Dask is a flexible library for parallel computing in Python. Now, that's what they say in the documentation, but what it means practically is Dask allows you to construct task graphs, and those task graphs interact with Dask's internal schedulers, which intelligently schedule when, where, and how tasks happen. And this allows you to scale quite flexibly from running on a single threaded laptop all the way up to a cluster. This has already gained some traction in the radio astronomy community, and in particular, DaskMS, which is integral in Cortical, is a way of exposing the measurement set, which is of course our data format, using Dask arrays and X-array data sets. So Numba is sort of the other half of the problem, which is how do we optimize the computationally demanding tasks? Because while Dask, of course, schedules tasks, it doesn't necessarily do anything to optimize those tasks. Numba allows us to speed up numerical code, a subset of Python and NumPy at least, potentially by orders of magnitude, provided we are willing to write C-like code that is using explicit for loops rather than array maths. And this is just a trivial example, so it's a just-in-time compiler, and this just shows how, with the simple addition of a decorator, you can speed up this Fibonacci calculation. So, does it work? Does Cortical work? Well, join me at my post to find out.
Hello, I'm Andrea Modigliani from ISO, and I present a poster on the high-level data reduction library, a library for ISO data reduction pipelines. This is a work in collaboration with our Australian colleagues of the AO, the Australian National University, and the Macquarie University. HDRL has been introduced at ISO in order to reduce the cost of development, verification, and maintenance of ISO pipelines, and to improve the scientific quality of pipeline data products. For example, adopting the HDRL response and flux calibration in UVES and Symphony pipelines enables Symphony pipeline to generate flux calibrated frames missing since several years before and improved the quality of UVES flux calibrated products. HDRL implements algorithms to determine by pixels, stack frames, compute over scan, Vestrel, and several others. It is already used by more than half of the ISO pipeline, the one here indicated in green, and will be used by even more pipelines, the one here indicated in blue. This year we have worked mainly on two areas. One is the implementation from the Australians of a model that computes and corrects the detector persistence. The persistence is an effort for which the remnant of a frame is imprinted on a subsequent image. This problem affects nearing detectors. These have construction defect that traps light-induced charges. The trapped charges decay with an exponential law with time from several hours to a few days, and in several cases may affect following calibration observation. We show three images. At the left, a dark frame affected by previous arc lamp exposure. At the center, a model predicted by HDRL. At the right, the corrected frame. The other project we have worked on this year is the pixel resampling of 2D images and 3D data cubes to a common grid. The pixel data are combined in a single cloud and later resampled in a single step. A user can also resample each data to a common grid and then combine the resampled data to reject outliers by median or kappa-sigma clipping. We show here two images. At the left, the combination of 100 OKI frames of a global cluster M30. At the right, 80 flexure frames used to test OKI flexure by rotating the camera by 160 degrees. A final word. We are happy to receive user feedback and proposal for the implementation of new common algorithms for scientific data reduction. This will be evaluated and possibly in the future implemented in HDRL. Thank you.
One, two, three.
The CAME3net experiments is a future European research infrastructure that will be located in the bottom of the Mediterranean Sea.
CAME3net detectors consist of strings, which are attached to the sea bottom and hold optical modules. So when a neutrino passes through the detector and creates another particle which is charged, which does emit Cherenkov light, we capture those with photomultiplier tubes.
These photon distributions serve as basis to reconstruct the energy and direction of the original particle. These particle events form the basis of our data. CAME3net will search for neutrinos from distant astrophysical sources like supernova remnants, gamma-ray bursts, supernovae, or colliding stars, and will be a powerful tool in the search for dark matter in the universe.
The ORCA detector of CAME3net is specifically optimized for the study of neutrinos created by cosmic rays in the Earth's atmosphere in order to determine neutrino oscillation properties.
The infrastructure will also house instrumentation for other sciences like marine biology, oceanography, and geophysics.
We aim to provide open source software for all our analyzing stages. We prefer to use open source software, and we also contribute to open source software. We use continuous integration to test our software, to deploy our software, and also to create documentation for our software. Most of our tools are simply Python packages which you can install using pip. We have a GitLab organization where we store our software for open access, but we also offer Docker images for more complex software. We also like using Jupyter notebooks to work with.
And we provide several examples of analysis.
We already published 10 years of Antares point source data through the CAME3net VO server, which includes event tables, detector acceptance, and background expectation.
We offer our data through our own open data center.
We also provide 1 week of ORCA4 data, which contains all reconstructed particles with 4 detecting units of ORCA.
And also the few snippets of acoustic data from one hydrophone.
If you're interested in listening to the deep. What can you do?
Come to our Open Science portal and discover the world of CAME3net science.
Find out more about how we process the data. Find out more about the software you use. In the CAME3net education portal, you can find tutorials, courses, and other video material.
Use our software. Use our data.
Please find bugs in our software and fix them if you have time.
Use our data and do amazing science.
1, 2, 3.
4, 5, 6.
Hello, now that you have seen the poster, I would like to show you a short slide demo of the CDS virtual SIA2 service. Let's start from a DSS color view of Galaxy in GC6946. I now open the simplified menu of the service and select all images we can generate around the Galaxy center in a radius of about 20 arc minutes. I get a large number of rows in my response. More than 400 actually. The central position and radius is used both for selection and for forcing the spatial characterization of the images. The system also gives me over parameters, over all obscure parameters, and over axis characterization. For the time axis, I can select images, the time range of which intersects a given time interval. Here I choose the date of November the 8th, 2015, 5 years ago. I get a lot of HST images in the response. Again, if I select between 500 and 800 nanometers, I find all red or near-infrared images, including Subaru, which is loaded and displayed here. The last two parameters allow me to reproject and rotate the output image in whatever projection and direction. Here is the DSS red in scene projection and position angle of 45 degrees. Here is the pan-starred red in the same projection and orientation. This view shows the subtraction of the two images. You can test it yourself and send feedback. The prototype URL is here, and I can provide you with the simplified menu for Aladdin on request. Thanks for your attention.
Hello and welcome to my poster about the virtual VO dissemination going on at the moment. So we're a big team behind all the work. We come from different institutions across Europe, and we work together under the umbrella of the ESCAPE project, which is a large European project to bring astronomy, astroparticle, and particle physics data into archives so that everybody can access them in a simple and easy way. Now, within that, our aim is to tell the people about the virtual observatory, the virtual observatory protocols, how to best use them, how to get the most of the archives, get all the data they need. And at the same time, we hope to get feedback from the community to understand what they need, what works for them, and so on and so forth. And we've been doing this for quite some time now, and so far our methods have been hands-on workshops, booth and demos at conferences, really getting to talk to people about what was going on. And more recently, our methods have slightly changed. We now do everything in virtual. We're currently planning a virtual hands-on school where we'll work collaboratively on attendees' science use cases. Some of us have given virtual tutorials, published blog posts, and just curate material collections online so that everybody can access them. And yeah, just to give you a bit of flavor of what we're doing, I'm going to quickly hop through all the tabs I have open in my browser. So our friends at SVO, they've organized, they're already in the midst of organizing and presenting schools to students and amateur astronomers. Mark Taylor from Bristol has given tutorials online. And at the CDS, we've been quite busy publishing a few blog posts on AstroBeta. Over at Gabo, they've been for a long time curating VO tutorials, putting them online where everybody can find them. And a similar thing is happening on the EuroVO page, which still looks like this, but not for very much longer. We've been finally able to update it, give it a new look, and soon you'll find everything on there as well. So if you're interested, come have a look at my poster, and I'm happy to chat with everyone on Discord or send me an email or all the other virtual ways you can think of. Thank you.
Hello, now that you have seen the poster, we would like to show you the potential of our observation splitting plus OBSTAP prototype. The first slide summarizes the content by a few numbers. The 14 observations have been split into 400 different datasets by our split algorithm described in the poster. I also give you here the frequency range. In this slide, using the tap handle interface to the OBSTAP service, you can see how we can select all datasets belonging to a single observation by using a constraint on the OBSID column. Now I concentrate on the characterization part of the response of this query, where you can see the spatial characterization there, the time characterization in modified Julian day, the wavelength characterization, and the frequency limits, which are part of our radio visibility metadata extension to OBSCORE. By loading the access URL, we display the data link response, including access to the full measurement sets and to the UV coverage plot, which you can see here. This query, using TopCat interface, selects datasets obtained with European VLBI network facility. The response contains one observation splitted in 5 datasets, 1 per field, and another one splitted into 20 datasets because some spectral windows are separated by little gaps. This query now selects datasets with higher frequency lower than 300 MHz or 300,000 kHz. The response contains 3 LOFAR and NUFAR calibration observations. One of them is splitted into several datasets because it contains separated spectral windows. This query, using Aladdin interface, selects datasets with large field of view, larger than 1 degree actually. And the response contains again LOFAR datasets. Aladdin allows to overlay the field of view on top of an all-sky DSS image. Thank you for your attention.
I will present you Opus, which is an interoperable job control system based on VO standards. In this poster, I explain that it is composed of several parts: a web client that communicates with a web server to execute jobs on a work cluster. The interfaces between those modules follow standards like the Universal Worker System, the Provenance Data Model, and uses SLURM and the SCIM standards. There is a documentation online, accessible here, where you have information on how to install it and configure it. Here is the web client, where I can have access to the job list, select a job among those, for example, gamma pi spectra. I will ask the server to run the job with those parameters. And once submitted, the UWS server is sending the job to the work cluster, and it is now executing. See that I am connected as the Opus administrator, so I have access to some preferences, the client accounts, and the definition of the jobs on the server. I can edit the job definition for this job, gamma pi spectra, and this follows the provenance data model description of an activity. I expect a few parameters, configure here, input data, and results. And here is the script that is executed on the work cluster. The job is executing, but we can see the properties, the parameters, and now that it just terminated, I have access to the results and the preview if it's an image or a text. I can also see the provenance, and I will show this for a test example, this activity. And the provenance graph for this activity, this one, activity 2, will go up to the raw data or the raw activity used, explaining the activity description and the parameters that are used for each activity. Thank you for your attention, and see you at the EIDAS.
Good day everybody, my name is Benjamin Neger. I'm presenting our optimized parallel flagger called Tricolor. This is a flagger for the Meerkat Radio Telescope in South Africa. It's developed by a collaboration within the South African Radio Astronomy Observatory and Rhodes University. Special thanks go out to the EIDAS organizers for this opportunity to present. The flagger is a fully configurable flagger that is based on the original sum thresholding algorithm by Andrea Fringa. you can specify and combine multiple sized flagging windows through a YAML-based strategy. Now, we've implemented our flagger within the task graph system, which is a Python library. It's parallelized over antenna pairs and scans, given that you have enough memory to do that. The kernels themselves, the algorithm itself is implemented in Numba. There's a Python-like syntax that is just-in-time compiled, which gives us C-like performance. We can flag all the way up to about 400 gigabytes per hour with typical strategies, about 4 times the typical dump rate for the coarse 208 kilohertz channelization resolution for the Meerkat correlator. This is quite a memory-intensive algorithm, but it still scales well all the way up to about 20 physical cores. The flagger is part of the Meerkat Science Data Processor, which is an online pipeline that produces science results, as well as our configurable offline pipelines with the Meerkat pipeline and the Caracal pipeline. For the latter, see the poster by Josh. And I'm going to leave you with some clean bands for the UHF system and the L-band system on the left and right, respectively. Here we're dominated primarily by positional satellites and within L-band and the telecommunications band, GSM 900 band within both the UHF and L-bands. Thanks so much for your time. If you have any questions, feel free to chat with me on Discord.
Fantastic. Thank you so much, Simon. Simon. Great idea. Great job. We'll end this webinar and we'll see you in half an hour for the virtual visit to the Calar Alto Observatory. And I will post the links to the new webinar and YouTube thingy in just a couple of minutes. See you soon.